Okay, so I got cut off there last time. But anyways, so remember, temperature has an impact on a material. Okay, so if I have a rock and I put that rock underneath heat or pressure, okay, can actually, depending on how much pressure it is or how much heat it is, it will react either brittly or ductily. But also the type of rock or the type of material it's made up of has a big impact as well. This silly putty is going to flow a lot better because it bonds differently than the quartz that I have in this metamorphic rock we call quartzite. Okay, it's bonded quite rigidly, whereas the bonds that are in these ones are weaker bonds to allow it to flow like this. Okay, so because of that, different materials will flow based off of the different bonding or the material it's made up of. Okay, so if you have something like a rock here, and let's say there's two different types of deformation, brittle deformation or ductile deformation. Well, if it's ductile deformation, the material will what we call bend and flow and cause what we call folds in the rock, like this. Whereas if it's going to break, we call that a fault, right? So if it breaks pretty rapidly, it will break apart and then break apart throughout there, and that's a brittle deformation. Now, faults are favorable in places where you have low pressure and low temperatures, relatively speaking. Okay, so still big enough to actually break the rock, but not enough high enough temperatures or something like that, and cold enough that it would actually act brittly and not ductily. Whereas folds tend to form deep in the earth, where you have ductile deformation. Okay, so high pressures and high temperatures. So here, favorable rock types that will break more brittly will be like sandstones, limestones, igneous rocks. They don't have as much give as some of these other rocks, whereas salt, shale, slate, and schist, those are those ones that are made up of like muds and small particles like that, have more bend to them. They'll ductily bend more than these rigid rocks will. And also, something that's ductile will, if you have slow deformation rate, okay, it's going to bend more, whereas if you have fast, it's going to actually be more brittle. Okay, so when we have these structural terms, or this terms of stress, also relates back to plate tectonics. Okay, so for example, if I have this block, let's say this was a block of crust, and with this block of crust, I start to actually cause what we call tensional stress or strain by pulling it apart, like in a divergent plate boundary. What's going to happen to the thickness of my plate? Well, it's going to get thinner, right? So it's going to get thinner and longer. Okay, so the overall thickness is now thinner, and it's been extended out. Okay, that's what would happen if you had ductile deformation. If you had ductile deformation, it would thin out and extend. Well, what if I were to have compressional deformation, or pushing it together? So if I have this material here, I just put it back into its state that it was in before. Okay, and now I compress it, and it's ductile. It's going to do folds. Now that would be something in like a convergent plate boundary. Okay, so you tend to have folds at convergent plate boundaries. You tend to have these pulling apart and thinning at divergent plate boundaries. Now at transform plate boundaries and a ductile deformation, it's the same kind of thing as you might have for compression, but instead you're bending. I should show this to you in the video here. Okay, here's my material, and then I slide it past one another. Okay, it has this shear motion, so it gives this kind of sideways fold to it. Okay, so that's ductile deformation if you have things underneath high pressures and high temperatures. Okay, so let's do a quick review question here. When a rock is subjected to high stress and high temperatures, they tend to undergo what kind of strain? Ductile or brittle? Now hopefully you remember that if it's high temperatures and high stress, it's going to be more apt to do what we call a ductile deformation or ductile strain. whereas shallow depths and low temperatures tend to undergo more of a brittle strain. So the right answer on this one is B here, ductile strain and brittle strain. Okay, so this is kind of getting you to make sure you understand the topic. Now, like I said, we've already talked about the ductile portion of this, but and then we call those folds. Okay, we have these bands or of material and acting in a ductile formation. Okay, now what I have these blocks. These are some wood blocks that I made, and if I actually put pressure on this one, where now I'm going to still do extension here. I extend it. Notice it's acting brittly in this sense, and we call these faults when they actually they're moving across one another. We'll give you the definition of that in a second. It's basically, well, you can see it on the screen here. It's the fracture in the Earth's crust along which rock units were displaced relative to one another. So there's been movement along that fracture, okay, and that's what we call a fault. Whereas a joint is just where you have had a rock that has a fracture in it. Doesn't necessarily mean that there's been any movement. It just has a fracture been broken. Whereas a fault is that there's actually been movement along it. So if I had a extensional regime, like at a divergent plate boundary, you get these kind of faults. We call them normal faults, and I'll show you how to identify those in a second here. Whereas if I and notice that the overall thickness if I took the average thickness of the crust, it would be thinner. If I took the average thickness, because down there in the center where they come together, they're thinner. Where before they were all the same thickness across. Now it's thinner averagely, but it's also been extended, just like when I did it with the ductile. Now if I push, now I have compressional stress, right? Okay, and this time, once again, the crust has been shortened, but has thickened. Okay, and so we call these reverse or thrust faults, and we'll talk about that one in a second. Now, if I had the same thing being sheared in a brittle formation, it would be moving like this, side by side, and we would call that a lateral shear, okay, or translational stress. Okay, so those are some examples of different types of stress. If it's brittly, we tend to form faults. When it's ductile deformation, we tend to form folds. Okay, so we've already talked about the joints a little bit, but these are cracks in rocks. We're going to talk about the brittle deformation first, and we'll come back to ductile deformation and the landforms that they form. In brittle deformation, often we'll get what we call joints. And here's some examples. This is the joints here in Arches National Park in Utah. And you can see the joints or the fractures in the rocks going in this direction through the rocks. You can see all the different areas. And this is why the arches form, is because there's this area of lots of these joints. You can see the joints in this vertical cliff of the shell and the cliff that's faced here as well. It's been pushed so far hard that it actually broke. Okay, there hasn't been any movement along it to form what we call a fault, but it's been broken. It just broke in place within the rock. We call that a joint. It's a natural crack in the rock. Okay, so however, a fault is where you have a surface. It's a surface of slip or change. Okay, so it's where that rock has actually been moved or displaced. Okay, so this block here has moved up relative to the other block here, which has moved down. Okay, we call that a normal fault, and I'll explain that a little bit later. Whereas if we go the other way, this block has now moved up relative to this one, and that's a reverse or thrust fault. And you can see those examples here in this picture here, where you see this block has moved down relative to this one. You can see this bed is up here, and now it's down here. So this is the actual fault surface right here. Okay. We call it the fault plane. And then it's actually moved down, or the displacement is the change in elevation that it's had from one bed to the other. Okay, so you can see that in that diagram here. Here's another example of one, but this is to go in the opposite direction. Instead of it going down, this block going down relative to this block, and we now have this block on the right going up over the other block, and this one would be what we call a thrust or reverse fault. Okay, so where they used to be together, and now they've actually been going over top one another. Okay. Okay, so let's explain the differences between a normal and a reverse fault. Okay, so to do that, I want to move ahead to this slide, and we'll come back to that other slide here. When we describe faults in what we call dip-slip faults are the ones that move up and down relative to one another. Okay, and we have two different blocks in part of this fault. We have this block here and the top block here. Okay, the top block, the one that always is on the top of the surface. Okay, faults are always in some kind of an angle usually, and the one on the top is what we call the hanging wall, and the one on the bottom is what we call the foot wall. This is an old miner's term, and the reason is because miners used to want to mine around faults, because these are cracks in the Earth's surface. Fluids would come up in them, and gold and things like that would actually solidify along these faults. Right? We talked about that when we talked about minerals and the different types of rocks. And so the block on the top is where their head is, where they'd be hanging from, right? And the block on the bottom is where their feet would be. That's what we call it a foot wall block. So the hanging wall block, the foot wall block. Okay? And so that's the different terms here. Now, some people get confused. If I all of a sudden turn these around, okay, which one is the hanging wall, which one's the foot wall? Well, the one that's on top is always the hanging wall. The one that's on the bottom is always the foot wall. So this is the hanging, this is the foot. Turn it around. Okay, it just got flipped, right? Okay, so this is the hanging, this is the foot. Makes sense? Okay, so now when the foot wall goes up relative to the hanging wall, or if I want to say that different, the hanging wall goes down relative to the foot wall. It's the same thing. I just said it reverse. That's what we call a normal fault. Now notice, to actually get this fault, I had to move it apart. Okay, so that's your divergence, right? Move it apart. The two blocks have to be moved apart for that to happen. Okay, we call that a normal fault, where the hanging wall goes down relative to the foot wall, and the foot wall goes up relative to the hanging wall. Normal fault. Now, if I go that's often for divergent boundaries or something like that. Now, if I go the opposite direction, okay, is the hanging wall has now gone up relative to the foot wall, or the foot wall has gone down relative to the hanging wall, we call that a reverse fault. Okay, when the hanging wall goes up, it's a reverse. When the hanging wall goes down, it's a normal. Okay, and so now realize that faults aren't always correlated with plate boundaries. A plate boundary means that that fault goes all the way through the lithosphere. Okay, so the whole plate acts separately from another plate. Faults, though, can actually be throughout the plate. Okay, we have faults here in North Carolina, but we have no plate boundary here. That means those faults that we have here in North Carolina are planes of weakness, but it doesn't go all the way through the crust, all the way through the lithosphere. So faults can't. So all plate boundaries are faults, but not all faults are plate boundaries. Do you get that? Okay. So the plate boundary goes all the way through the crust, and we still call that a fault, but because there's been movement on either side. However, sometimes that fault doesn't go all the way through the crust, and if it doesn't go all the way through the crust, it's just a fault. It's not a plate boundary. Okay, that's the difference between the two. However, places where you have divergence, okay, moving it apart, you're going to have more normal faults. When you have them going together, you're going to have places of reverse faults, right? Okay. So I showed you this one on the last one here. We put the hanging wall goes up, normal. Hanging wall goes. The hanging wall goes up. That's reverse. Hanging wall goes down. That's a normal fault, right? Now, if I had the other one, the last one's just a strike slip, they move past one another. Okay. Now, if the block here, let's say I'm here and looking across the block. If it moves to the right, we call that a right lateral fault. If it moves to the left, we call that a left lateral fault. Okay. Now, notice if I was on this side looking this way, it would look the same way. It would move to the left, left lateral, right lateral. Okay. So it depends upon the relationship of the block to each other. And these are what we call strike-slip faults. They're related to transform faults in a way. Okay? So those are the type of faults. We're going to come back to talk a little bit more about this in just a bit.